classification. Now let's talk about regression. Regression is different. In classification, we had a fixed number of labels, and we were basically counting how many times are we right, how many times are we wrong. With regression, you can't do that. You're predicting numbers, so you are always going to be wrong. And the question is not really how many times were you wrong, it's how much off, by how much were you wrong. And in regression, what you're usually doing, so here's an example of regression. You have two attributes, x1 and x2, and you're trying to predict the y value. The black points, they correspond to the real observations, right? So that's the real value y at a certain combination of x1 and x2. That's what you see in the data. And the plane that you see here, that's a linear fit to the data. So that's what you get out of linear regression, the last lecture that you had with Nigel. Linear regression would predict those values on the plane, and what you're trying to see is you're trying to see how close is that plane to the data points. And the way you measure it is you basically look at how far away, what is the difference between the real y value and the y value predicted by the hyperplane. And the y value predicted by the hyperplane, that's just if you take this and drop a line straight down. That's the predicted value where it intersects the hyperplane. So what you want to measure in regression is how far off the hyperplane is from all the observed data points. So it's some measure of distance between the true values and the predicted values. And there are several different ways of measuring it, and we're going to talk about three sort of big families of ways. The most common way is mean squared error. So mean squared error is you take the difference between the true value and the predicted value, you square it, and you add it up over your testing set. So that's the sum squared error. If you divide it by n, the number of testing instances, you get mean squared error. If you take the square root of it, you get root mean squared error. All three are used in various ways. You have mean absolute error. It's similar. You are taking the difference between the predicted value and the true value, but now instead of squaring it, you take an absolute value. Why do we need an absolute value?
Because some values are negative and some are positive.
Yes.
So
exactly. So some differences will be negative, some differences will be positive. If they cancel each other, that doesn't mean that you have an error of 0. You could have a very large error that cancels out. That's not a good thing. So that's why you take absolute value. And the square root here plays the same role as an absolute value. It makes everything that was negative into a positive number. Very similar thing, only you're not squaring the differences. And we'll talk about the reason for that. The reason for that is that helps you deal with outliers in a slightly more sensible way. And then we have a correlation coefficient, which looks really, really different. But it's actually kind of a similar idea. So what you're doing in the correlation coefficient is instead of taking the difference between the predicted and the true, you take the predicted and subtract the prediction mean. You take the true and subtract the true mean, and then you do a dot product of those things. So I'll talk about what that means, and then you normalize by the product of the standard deviations. So in relative terms, so mean squared error, very sensitive to outliers. Mean absolute error, a lot less sensitive to outliers, but still very sensitive to the mean prediction and the scale of predictions. And correlation coefficient is completely insensitive to mean, completely insensitive to scale. It is sensitive to outliers, though.